Thanks for watching Edupedia World videos. This is the second video in the topic of diodes, and in this video we'll learn various uses of diodes. Let's begin with a diode as a rectifier. Now, in our unit on electricity and magnetism, we've already seen what an alternating current is, and a rectifier is something which gets a direct current or a current in only one direction from an alternating current. And the property of the PN junction diode that is used here is that it only allows current in one direction and has a very large resistance in the opposite direction. So there are two ways you can do it. The first is called half wave rectification. So this is the symbol for an alternating current, and the graph for an alternating current would go something like this. V versus time would be, if it's a sinusoidal current, it will go like this, and generally alternating currents are sinusoidal. So what we do is we attach a PN junction diode to it, or any form of diode, but right now we're talking about PN junction. We've already seen that this is the symbol for a diode, where the arrow points in the direction in which the current is allowed to flow, and there will be some resistance. Let's say the resistance is R. So whenever this is at a negative potential and this is at a positive potential, then this diode will be forward biased and it will allow current to flow through it, and the amount of current flowing through it will simply be V by R. And if V is equal to V naught sine omega t plus phi, then I is equal to V naught sine omega t by plus phi by R plus Rj. This is R total. Rj would be the resistance of this junction, which we know is very small in the forward bias direction. So we could even actually neglect it, and there would be the current flowing V naught sine omega t plus phi by R. Now after half cycle, this will be positive and this will be negative, and now the diode is reverse biased. And when the diode is reverse biased, this R is extremely large, meaning this current is almost zero. Right. So the graph of the voltage across this current, across this resistor, would actually look something like this. A half cycle, then no current. Then a half cycle, then no current. Then a half cycle, then no current. Half cycle, no current. This would be the current, or even VR, the voltage across the resistor R with respect to time. What would VR be? VR would simply be R V naught sine omega t plus phi by R plus Rj. When Rj is small, this is equal to V naught sine omega t plus phi, or this value in the forward bias direction. When Rj is very large, this is approximately equal to 0. And this is called a half wave rectifier because it gives us half wave loops from a full alternating current. What if we wanted to have full wave loops like this? In that case, we can use the second type of rectifier, which is aptly called the full wave rectifier. And in this case, you'll need two PN junction diodes. At any point, one of them will be forward biased and the other one will be reverse biased. I'm sorry. And in this case, we want a full wave rectifier across this R. Actually, I've made this look like an inductor. This should be a resistance. Right. So let's say this is negative and this is positive in one cycle. We already know what the graph of the input voltage is going to be looking like. So during this half cycle, this is negative and this is positive, and this junction is forward biased, whereas this junction is reverse biased. right? Because this is negative, we'll assume this to be 0 potential. If this is positive, this is forward biased and this is reverse biased. So current will flow in this direction, and since this is reverse biased, no current will flow here. So all the current flowing through this wire will come out through this resistance. So there will be a current through this resistance. Now let's turn it back, and now this is positive and this is negative in the second half cycle. Then this is reverse biased and this is forward biased. So now the current will go in this direction, and again, since this is reverse biased, no current will flow through this junction, and this current also will come out in this direction. So in both the cycles, the current through this resistor is towards from the right to the left, and hence the voltage across this resistor would look to us to be something like this. And this is called a full wave rectifier. Now another important use of PN junction diodes is to use them as a transistor. Transistor basically is a device like a PN junction diode, and that can be used for purposes like amplification. So first let's study what a transistor is. A transistor is basically formed, there are two types of transistors, NPN and PNP. And you can actually easily tell from the name how they are constructed. You take a small, the middle one is always thin, remember that. So you take a, let's look at NPN for now. You take a small thin layer of p-type semiconductor and you sandwich it between two n-type semiconductors. So NPN. This is the standard NPN transistor, and unlike a diode, a transistor actually has three terminals coming out of it. This would be the Pnp transistor. Now don't confuse this with the depletion layer. Both of these junctions would have their own depletion layer. The middle thing is not a depletion layer, it's a third form of semiconductor sandwiched between the first two semiconductors. The middle layer is called the base in both these cases, and the base is very lightly doped. That means the amount of concentration of either the donor ions or the acceptor ions is very small. Now out of the other two layers, one is very heavily doped. Let's assume that is the left one in both cases, and that is called the emitter. And the other side is moderately doped, both still with a higher doping than the base, and the other side is called the collector. Terminals come out from all the three layers so that we can connect them externally in a circuit. How they are denoted in a circuit is like this. The NPN one would look like this. This would be the collector, this would be the emitter. And the arrow between the base and the emitter actually tells us whether it's an NPN or a PNP transistor. The arrow denotes the current flow from the emitter to the base or the base to the emitter. So let's have a NPN junction. In an NPN junction, the current would go from the positive side to the negative side, right? So it would go from the base to the emitter. So this is the symbol for the NPN junction, and this is the symbol for the PNP junction. Remember, PN junction diodes only conduct current in the forward bias direction. So this junction would conduct current if the P side is forward biased and the N side is on the negative side, and the current will go from the P to the N or from the base to the emitter. In a PNP junction transistor, it goes from the emitter to the base. So this is the NPN transistor and this is the PNP transistor. Usually the emitter base contact is much smaller than the base collector contact, and a realistic diagram would probably look something like this. Emitter, base, collector. The contact area between the base and the collector is generally higher. In the normal generic operation of the transistor, the emitter base junction, this junction, is forward biased, and the base collector junction is reverse biased. Right, so this is something you need to remember. Emitter base, is forward biased and collector base is reverse biased. Now there are different configurations in which a transistor can be used. We'll study three of them, and by default, unless otherwise mentioned, we'll assume the existence of an NPN transistor. So it can exist in three different modes depending on where the earthing is or where the potential zero is. Now the first mode is the common emitter or the grounded emitter. And this is the standard working of a common emitter. This is the common emitter mode. Just like you have a forward biased and a reverse biased mode, you have common or grounded emitter modes for a transistor. This is the base going to the emitter. From the arrow you can tell which one of these is the emitter. This one is obviously the base because it's in the middle. And I'm going to draw three different modes here: common emitter, common base and common collector. And I'd like you to verify that in all three of them the emitter based junction is forward biased and the collector based junction is reverse biased. So we assume this to be the grounded V is equal to 0. This has a potential V1 and this has a potential V2. This is the emitter. And for the emitter based junction to be forward biased while collector based junction to be reverse biased, we need to have V2 greater than V1. I'll let you verify that on your own. So this is the common emitter mode. Now I'll just rub this and draw all three modes together. There is the common or grounded emitter mode, CE, common or grounded collector mode or CC, and common or grounded base mode, CB. And the common one basically means we assume the potential of that to be 0. In this case, it doesn't matter whether the magnitude of V1 is greater than V2 or V2 is greater than V1, because it will be forward or reverse bias appropriately in any case. This is the smaller terminal, this is the bigger terminal. So this is the common collector configuration, and then you have the common base configuration. And here for the appropriate configurations you would again need V2 greater than V1. So let's look at the standard working of the transistor. The most widely used is the common base mode, so that's what we'll study it in. Also, it's easier in the common base mode because you don't need to worry about which one is greater out of V1 and V2 because they're in opposite directions. Right, so emitter, let's do this, the emitter base collector. You can see that we've assumed an NPN transistor, so sorry, this is my mistake, this is the base. So you can see the base is at a lower potential. Yeah, that's not right. this should be opposite. You can verify it from the previous figure. Yeah, so now if this is 0, this is negative, so the base emitter junction is forward biased and the collector emitter junction is reverse biased. Let's call this VEE and then let's call this VCC. Let's say there's a current IB flowing from here, there's a current IE, emitter current, and there's a collector current IC. Now, since the current is flowing from the base to the emitter, that means electrons are going from the emitter to the base. But since the base is actually very thin, most of the electrons going from the emitter to the base will go directly to the collector. A few of them will come outside from the base, but most of them will go to the collector. So by KCL we can see that IE is equal to IC plus IB. But generally most of the current of IE will go into IC. A small amount, maybe 1 to 5%, goes as IB. But most of it goes as IC, and that is because we have a very thin layer of base sandwiched between the emitter and the collector. IE is the emitter current, IC is the collector current, and IB is the base current. There are two parameters which define the working of a transistor or characterize the working of a transistor, and they are called the alpha and beta parameters. The alpha parameter is equal to IC by IE, and it is typically about 0.95 to 0.99. Most of the current going from the emitter, most of the electrons going from the emitter into the base directly go to the collector. Then you have the beta parameter, which is IC by IB, and that is typically 20 to 100, because IC, the current, will be much greater than IB. And if you use this equation, you'll be able to verify on your own that beta is actually equal to alpha by 1 minus alpha. Right. So this is the standard working of the transistor, and these are the two parameters which characterize the working of a transistor. Now, a very important use of a transistor is in amplification. When you have a small signal and you need to convert it to a larger signal. A small input voltage signal has to be converted to a larger input voltage signal of obviously the same structure. So we'll see the working of a transistor as an amplifier now. And for an amplifier, a transistor is used as the Npn transistor in common emitter mode. So let me just draw the figure now. It might take a little bit while. This is the input voltage Vi, and this is the voltage we would like to amplify to a bigger value. This current going in will be IB, the base current, because this is the base, this is the emitter, this is the collector. This current going here will be IC. Remember, the collector base junction is reverse biased. And this resistance will be RL, the load resistance, and the voltage across the load resistance will be our output voltage Vout. And you have the emitter connected here as well. So this current will be IE. This potential difference will be VBE. I'll just make it a little bit clearer. And this total potential difference will be VCE. So this is the potential difference between the emitter and the base, and this is the potential difference between the emitter and the collector. So now what happens in an amplifier is that the electrons diffuse from the emitter to the current. That's why the current is from the the emitter to the collector. That's why the current is from the collector to the emitter, and this ends up creating a negative charge at B, because some electrons will be stopped at B and or will go from B to this side, right, from the base. So this creates a small negative charge at B which tends to block further electrons. If we send a very small current IB in this direction, then that electron negative charge will be neutralized and we get a large current IC. And that is basically the principle of amplification. So I'll explain it again. Electrons are going from the emitter to the collector. That's why the current is from the collector to the emitter. Those electrons stay for a while at B, and this ends up creating a negative charge around the base. And that negative charge actually stops more electrons in going from the emitter to the collector, and so there's a steady state current which flows. However, if we just give a small positive charge to the base, it will neutralize that negative charge and we will have a very large collector current. So a small change in the base current gives a very large change in the collector current, and that is the principle of amplification. Small change in IB implies a large change in IC. Right. So if the input voltage Vi is, let's say, a loudspeaker or something like this, then the output voltage V0 will end up being something like this. It will have the same period, of course, but it will be greatly amplified. And the parameters for this transistor used as an amplifier are: the first is the current gain, which is symbolized by beta. That is equal to approximately 50 usually. That means a small change. I forgot to write what this is. This is delta IC by delta IB. We saw beta for a pure transistor was IC by IB. Here we actually look at change in IC and change in IB. And a small change in IC actually roughly gives around a 50 times change in IC. Right. Now delta VRL, which is the change in potential across this, delta VRL, will actually be V out, the output voltage we want, and that can be written as RL delta IC, the load resistance multiplied by a small change in IC. Right. And as the base emitter junction is in forward bias, it offers a very small dynamic resistance. We can have RBE be equal to VI by IB. Right, that is the resistance here between the base and the emitter, the small resistance offered. This is referred to as the input resistance of the circuit. So from that the equation we get is, I'll just rub this, it's taking some space. Input resistance of the circuit is RBE. From that we can get a little bit of math now. Delta IC is equal to beta times VI by RBE, which means delta VRL is equal to beta times RL times VI by RBE, which tells us what this is V0. So what is V0 by VI? That is equal to beta RL by RBE, and this is what is called the voltage gain. This is the current gain beta, this is the voltage gain. And we already know beta is around 50, and if we take RL to be much greater than RBE, then the amplification can actually be very large. Right. Then there's another term that is defined for these transistors used as an amplifier. We have current gain and voltage gain. The next is the power gain, and that is simply the current gain multiplied by the voltage gain, and that will come out to be beta squared RL by RBE. Right, this thing multiplied by this thing, because we know power is equal to current into voltage, so it's reasonable for us to say that the power gain will be the current gain times the voltage gain. There's one final quantity that is left, and that is called the transconductance of the amplifier. Sometimes it's also called the transfer conductance, and that is GM and that is equal to delta IC by delta VBE. The unit of transconductance is MHO, mho, and 1 MHO is equal to the inverse of 1 ohm. Right, so transconductance has the dimension of conductivity, just like resistivity has the dimension ohm. Sorry, transconductance has the dimension opposite to that of resistance, not of that of conductivity. Right. So this is another major use of transistors. You can actually have a small input voltage here which leads to a small current, and that can actually create a very large current across this, and so it can be used as a voltage amplifier. This completes our analysis of transistors and diodes. Thank you.